All right, so that's pretty clear, right? With a one-dimensional example, we can see it, we can graph it, we can visualize, we see the moment where the model becomes good, right? But how do we understand this goodness, or this quality, or this performance, right? That was our metric that we set up for knowledge, it's performance. How do we understand performance quantitatively? Because this works for a one-dimensional data set. A lot of the data we're going to be looking at has many features, right? Even with the people, there's 3 features. There's gender, height, income. You can have potentially hundreds or thousands of features, right? So these are fundamentally multidimensional problems that we're not going to be able to graph. So how do we understand the performance of these systems when we can't evaluate it visually? Well, the typical approach is mean square error. For each point, you look at the difference between the value in the point and the predicted value. So in a graph like this, it's the distance between the point and the line. For any value of x, the line is where the prediction is, and the point is what it actually is. So you look at each of these distances, right, as values. The bigger the distance, obviously, the more error. You square that error because you want to penalize points that are farther from the curve more than points that are closer because you want to get rid of outliers. And squaring, by the way, also handles any issues with negative numbers. And then you normalize that by the number of all points. So that's the mean. So it's the average square error in your model. Right? It's how far the model is from your actual points. This is a very typical type of performance criteria. It's used in all statistics, but it's also the one used in machine learning. So it's just another way that this is really not anything new. These are how these things are analyzed as well. So now we can look at our 3 models, right? Here was the constant, 0 degree, best fit line, best fit cubic. Here we have a plot of the mean square error. Okay, we see a lot of error for the 0 degree, for the constant, decreasing error for 1 to 2 degrees, and then 0 error here for the cubic. Okay, so we actually don't need this curve. We can run every degree model through this data set and stop when we get to 0 error. For a perfect data set, this works really well. Does that make sense about performance analysis? This is going to become really important really quickly. So